Hello everyone, here's a video on IB Advanced Higher Level topic 9.1, and more specifically we're going to talk about the velocity equation. So if you've been following along so far and in class, we've covered a bunch of these equations. So here's our equation list from our data booklets, and just to tick off some stuff, we've done the angular velocity, we've talked about the acceleration formula. We've derived all of these through a little bit of calculus and looking at some graphs. The idea of today is to look at this guy here. This is the velocity equation. Hopefully we won't spend too long on it. I just want to derive it for you so you can kind of see where it comes from. And then of course we're going to use it on a couple of examples. Okay, so let's just restate some of the things we know. We know that in simple harmonic motion, the velocity is going to be equal to the maximum displacement multiplied by omega, the angular frequency, and then cosine angular frequency multiplied by the time. Remembering that cosine could equally be the sine value. It just depends where you start on your graph. It depends where you arbitrarily decide you want to start the motion. In addition, we can also say that the displacement in a simple harmonic motion is the maximum displacement and then sine omega t. These are things we've looked at before. And then acceleration, I probably should have done these in the other order, doesn't matter. Acceleration is the negative omega squared x. And what's probably important just to mention and reiterate again is at this point, hopefully we can see that acceleration of a simple harmonic motion would also be kind of equivalent to this negative kx. And so we've already said this, but we can sort of state it again. Really the spring constant, or the constant of a simple harmonic motion, is potentially equal to this omega squared. Other things to just reiterate, it's just worth again stating what we already know, is that when the maximum value, when we're at a maximum position in our graphs, we can say that the sine and the cosine value must be equal to 1. Okay, remember we talked about that before. What that means is that they can cancel out, and we're left with a couple of statements. We're left with this maximum velocity, which would be at this value of 1, is equal to just the maximum displacement times the angular frequency, and the maximum acceleration is equal to the maximum displacement times omega squared. We also just need to remind ourselves that when the acceleration is at its maximum, then the displacement must be in its opposite maximum state, and vice versa. So when our displacement is in its maximum state, then the acceleration must be the opposite maximum value. So these are all just conditions, statements that we can kind of play around with. Okay, so we can hold these in our minds. I'll just move them out of the way for now. And then to help us essentially use these statements in various different ways to get to this statement here, I'm just going to come back to the idea of a circle, and we're going to do a little bit of trigonometry, I guess, and just play around with some ideas and some statements to simplify or to restate essentially cosine theta in a different way. So I'm going to make a statement about cosine theta. So let's just put that down here. Cosine theta is right there. In terms of a circle and things moving in a circle, I also know that theta is going to be equal to omega t. I should be familiar with that by now. So what I can do with this is bring in one of my previous equations that we just looked at. Let's put it up here. My velocity equation, which is x naught omega cosine omega t. And of course, I'm just going to change this around. I'm going to say x naught omega cosine, but then rather than omega t, I'm just going to put theta in. Okay, so I'm just basically substituting this in. These are interchangeable because of the truth of this statement. Okay, and now what I'm going to do is have a look at what we can do with some trigonometry. So let's have a look at our circle. Here it is. Of course, I'm going to go and make some, put some things on here. I'm going to say this is theta. I'm going to say that this red arrow is r. That's the radius of the circle. And then let's go ahead and say that, of course, I'm going to try and do this nice and neatly. This length here we'll call y, and this length here we're going to call x. Okay, pretty straightforward. So I've got a triangle. Let's go ahead and say that the radius is equal to 1. So I'm just trying to redraw my picture here. This is 1, and then I've got my lengths, well, my components of the triangle. This is y, and this is x. Of course, with regards to theta, this length here is sine theta, and this length here is cosine theta. So adjacent and opposites, hopefully you can see that. Let's now play with Pythagoras' theorem, which is, remember, c squared is equal to a squared plus b squared, c squared being the hypotenuse. So in this case, because we've defined it as 1, oops, that's not a very good one. Because we've defined it as 1 squared is 1. And now I've got my a and my b are sine theta and cosine theta. And then if I rearrange this, I can make a statement with regards to the cosine. I can say cosine theta is equal to, now check this out, it's going to be plus or minus because we're squaring. Okay, so the plus or the minus, and then the square root of this 1, because that's my answer to 1 squared, minus the sine squared theta. This is neat. This is kind of cool. This is where the plus minus comes from. So we've got the plus minus because, you know, squaring a plus or a minus is, we don't know. It could give us either one. So we put them as options. It really just depends on how you define the system. In other words, we don't really know. You have to understand what the question is asking to really get at that. And you'll see that in a minute when we do some examples. It's going to be a plus or a minus depending on how you define your simple harmonic motion. If it's going up, you might call it a positive. If it's going down, you might call it a negative. It's kind of up to you. So you probably guessed it. What we're going to do is we're going to take this statement that we just made using our Pythagoras theorem, and we're going to insert this into these velocity equations. So what does that look like? Well, let's keep going. We'll say now that the velocity is equal to x naught omega, and then we're going to substitute that in. So actually, I'll just rearrange it slightly. I'll put my plus minus at the beginning, my plus minus, that's coming from our equation, x naught omega, and then the square root of 1 negative sine squared theta. Okay, so let's just leave that for now. We'll just put a circle around it. We're going to need this statement in a minute. Okay, moving on. Let's look at the other equation we started with, which was the displacement equation. So displacement is going to be equal to the maximum displacement sine omega t. Now, of course, we've already said that omega t is equal to theta, so we can keep going with that. We can say x is equal to x naught sine theta. Now we can just rearrange this to solve for sine theta. So sine theta is equal to x over x naught. And now I'm going to go ahead and just square everything, because look what happens if I do that. If I square everything over here, which means I've got to square everything here, I am left with a sine squared theta, which is convenient because look what I have up here. I have a sine squared theta, that also appears in my first equation or my first statement that I have here. So I've got a sine squared theta. Let me just go ahead and make that a little bit different. Again, just using our theta is equal to omega t. I'm going to say sine squared omega t is equal to my x over x naught, and I'll put it in brackets, squared. Okay, we're nearly there. My last job is to combine these two equations. So I'm going to take, well, I guess I could just use this one. Use this equation and combine it. So these two I'm going to be combined together. I'm going to take my sine squared theta, or it could be sine squared omega t, it doesn't matter which version you have, and I'm just going to combine these together and then simplify it down. So let's go ahead and do that. So we're going to basically take these two, merge them together, and we're going to get our velocity equation. So I've got v is equal to a plus minus x naught omega, and then the square root of 1 minus, just move this out of the way. Well, I did have sine squared theta, but now I can substitute that in for x over x naught squared. Now it's just a case of simplifying it down. So I'm going to go plus minus. And I'm going to do some factory stuff. Let's not worry too much about that, but that's going to leave me with I'm going to bring my x naught into underneath the square root sign. So I'm going to go, well, that's going to be x naught squared minus x naught squared all over the x over x naught whole thing squared. And we can cancel some things out here. And what are we left with? Well, we're left with omega, plus minus omega, and then the square root of x naught squared minus x squared. And that there is our equation that we were trying to get to. Let's have a look at it down here. There it is, our velocity equation. What do we need to do with that? Well, you may have just lost 10 minutes of your life listening to the derivation. I thought it was kind of worth it. It's kind of fun to do. But really what we need to do is just get used to using it, plugging some values in. So here we go with a worked example. This is just from your textbook again, so you can reference it whenever you like. But here we have an object, whatever that object is, we don't know, but it's oscillating in a simple harmonic fashion. We're given the frequencies and we're given the amplitudes. What we need to know is the velocity at a particular displacement. So let's just chuck some values in. I'm just going to visualize this. I always think it's worth drawing it out and seeing where this question applies to the foundations of what we've been talking about. So let's go ahead and say that this is a displacement graph. So this would be the maximum displacement up here and then the maximum negative displacement down here. We are given that. We're given the maximum amplitude. It's right here, 25 millimeters. Might also be useful just visualizing what this could even be. So let's just assume that it's an object on a spring bouncing up and down forever, since there's no friction. It's going to have a maximum and a minimum. Try and match that to the graph a little bit. Maximum and a minimum. That's the equilibrium position displacement. So right up here, this is the x naught, which is 25 millimeters above the equilibrium. And then down here, this is going to be 25 millimeters underneath the equilibrium. What the question is asking though, again, we should write down this as well. The frequency of this oscillation is 60 hertz. And what we're asked is with regards to a certain position. So it's saying, what is the velocity at position 8 millimeters from the equilibrium? So I'm just going to guess that it's about here. Let's just say that this is, not nanometers, 8 millimeters. There we go. About here. And of course, that's the equivalent of also asking for this velocity at this displacement. So whatever it is, this is the plus minus bit, right? So you can choose whether it's a plus or a minus. It just depends on where it is in the situation. The question is, what is the velocity at this 8 millimeter displacement? Well, this is where you need to recognize which equation to use. So hopefully you can see that that's where this velocity equation is going to come in. Let's present that equation just down here. So remember, from your data sheet, the velocity equation is this plus minus omega square root of x naught squared minus x squared. So we do have to do a little bit of a conversion. We have the frequency. What we need to know is the angular frequency or the angular velocity. So let's just do that over here first of all. It should be pretty easy for you. We know that the angular frequency is the time it takes to do 2 pi, in other words, 2 halves of a circle, and that's going to be the period. We also know that period is the inverse of frequency, so omega is going to be 2 pi f. So really all we're doing now is plugging it in. I can say that the velocity is plus or minus 2 pi f, the square root of x naught squared minus x squared. Let's go ahead and plug these numbers in. So it's going to be plus minus 2 pi, and then the frequency we're told is 60 hertz, and then it's the square root of the maximum displacement, which is 25 millimeters. So 25, let's convert that into meters. So 25 times 10 to the 3, we'll put it in brackets, squared minus the displacement that we're interested in, which is 8 millimeters. So that's 8 times 10 to the negative 3, and that's of course squared. If we plug all that into our calculators, we're going to get 8.9299 something something something, and that's going to be in meters per second. And what does that mean? Well, we need to think of significant digits or significant figures. In our question, we have 2 and actually only 1. So this is going to have to round up to a 9. So my answer here should be 9. Let's write it out. The velocity at the 8 millimeter displacement, whether it's going up or down, is going to be a plus minus, depending on whether I'm going up or down, and then just 9 meters per second.